Let us see about phase control rectifier or the fully controlled rectifier. In that we will see about half wave rectifier with R and RL load. So this is the classification of rectifier. We have already seen about uncontrolled rectifier, in that both half wave and full wave is completed. So here in uncontrolled rectifier diodes were used. Now we will see fully controlled rectifier which uses thyristor. So the difference between uncontrolled rectifier and fully controlled rectifier is that in uncontrolled rectifier output voltage cannot be controlled, whereas in fully controlled rectifier you can control the output voltage. Here diodes are used for rectification and diodes are uncontrolled devices. Here thyristors are used for rectification. And in uncontrolled rectifier always power flows from AC source to DC load side. But in fully controlled rectifier you have the option to send the power from load to source. So that we will see how a controlled rectifier works. In single phase fully controlled rectifier, SCRs are used. So it has three terminals, anode, cathode and gate. So when you apply a gate pulse, it gets turned on. So this is a rectifier circuit. You have AC input and you are taking DC output here. So SCR is connected here. During positive half cycle, SCR is forward biased. Only when you give the gate pulse, it will start conduction. So how to turn off this SCR? So during negative half cycle, it gets turned off automatically due to the reverse bias condition. So this process is called natural commutation. What is commutation? The process of turning off of SCR is called commutation. And when you have a AC input supply, SCR gets reverse biased and turned off automatically. This process is called natural commutation. Suppose we have a DC input here instead of AC, a DC signal is here. In that case, SCR cannot turn off automatically. You need some external circuit to turn off the SCR. In that case, commutation is said to be forced commutation. Let us see the applications of rectifier. It is used in various applications in our day-to-day life. One such example is locomotive system. You can see here, this is the symbol of rectifier. Okay. So this can be a single phase or three phase depending upon the application, but rectifiers are used. In controlled rectifier, the output voltage can be controlled by varying the firing angle. So what is the firing angle? It is the angle at which the SCR starts conduction, or the instant at which SCR conducts is decided by this firing angle alpha. So this IG, this blue color line is the gate pulse. So this can be given to this SCR gate. So once it is received, SCR will start conduction. So you can see from this waveform, as you delay this gate pulse, output will also get delayed. So if the waveform changes, average voltage will change. It means that output voltage magnitude will change. So this control rectifier actually converts the constant AC voltage into a variable DC voltage. And why it is called a phase control rectifier? The zero crossing of the supply voltage is here, but you can see the output waveform zero crossing is somewhere here depending upon the gate pulse. So you can control the phase angle between the supply voltage and the load current. So it is called a phase control rectifier. So now this is an important topic. Only if you know to draw the waveform, you can study power electronics actually. So this is a sine waveform because our AC supply is a sine waveform. So you should know to draw the sine waveform clearly. So, total cycle is 2 pi, that is equal to 360 degree. So half of that is 180 degree, that is pi. The center part is 90 degree. Here I have drawn the lines for every 30 degree. So this is 30, 60, 90, 120, 150 and 180. So you should know this sine table first. So sine 0 is 0, sine 30 is 0.5, sine 60 is 0.86 and sine 90 is 1. So remember these things, you can draw the sine waveform. And you can see that I have mentioned here pi radians and here in degrees. Normally we will use only radians. Okay. So you should know this angle to radians conversion also. So angle to radians. So 360 degree is 2 pi. So this is 360 degree, one cycle, that is equal to 2 pi. So if I want to know what is the radians for this 30 degree, use this formula 2 pi by 360 into this angle. So you will get pi by 6. So this point is pi by 6. This is 2 times pi by 6 and 90 degree is pi by 2, 120, 150, 180. So you should know this also so that it will be easy to analyze and draw the output waveform. So now let us draw this gate pulse here. That is at 30 degree I am applying the gate pulse. So how to draw the waveform for this one, output waveform? So you draw this input waveform, same input waveform in a dotted line or lightly you can draw this one. So over this one you draw the output waveform. So let me take the pen. Now I am giving gate pulse here at 30 degree. So till that SCR will not conduct. So output voltage is 0. Now it starts to contract. But what will be the waveform? Once it starts conducting, its waveform will be equal to the supply voltage. So you draw exactly over the dotted line. So this is the output voltage waveform. And negative half cycle, it is not conducting, so 0. Okay. So at 30 degree you are applying the gate pulse till that output voltage is 0. Then you should follow the input voltage waveform. Next we will do for another angle. Suppose I am applying the gate pulse at 60 degree. So one box is 30 degree, this is 60 degree. So let me change the color of the pen. So in this case output voltage will be 0 till 60, then follow the input voltage waveform, then 0. Okay. So next we will do for another. Suppose our gate pulse is at 90 degree. So in that case till 90 degree your output voltage is 0 and draw the waveform at 90 degree. Follow the input waveform till 180 degree, then 0 till 2 pi. Okay. So let me take one more example. So this is at gate pulse at 120 degree. So follow this waveform till this point and then becomes 0. So this is the output waveform at 120 degree. So now you can see that if you find the average value of this red one, it will be somewhere here. But if I find the average value for this blue color waveform, it will be somewhere down. Okay. The same thing, if I find the average value for green color, it may be somewhere here. For red color, it will be a very low value. This is how we are able to control the magnitude of the output voltage by varying the firing angle alpha. So this period, here alpha is 30, in this case alpha is 60, in this case alpha is 90, and in this case alpha is 120 degree. Now coming to the topic, half-wave control rectifier with R load. So this is the supply voltage. It is a sinusoidal waveform. We are giving the gate pulse at this point alpha, that is the firing angle alpha. So during positive half cycle, though SCR is forward biased, it will not conduct till alpha. Only if it receives the gate pulse, it will start conduction. So till that output voltage is 0. After that it follows the input voltage waveform. And during negative half cycle, it gets turned off due to natural commutation, and pi to 2 pi output voltage is 0. Now to draw the waveform across this thyristor, we have to follow the same rule as we have did for diodes. So when the device is conducting, output voltage will be, voltage across the device will be 0. When the device is not conducting, it will be equal to the supply voltage. So here 0 to alpha, thyristor is not conducting, so it is equal to the supply voltage waveform. So this portion, so this portion of the waveform will come. Okay. So here, then when it is conducting, alpha to pi it is conducting, so it is equal to 0. Then again pi to 2 pi it is not conducting, so it should follow the input voltage waveform. So it is equal to input voltage waveform. Again till 2 pi plus alpha it will not conduct, so the cycle repeats. This portion will come. Okay. And here in case of thyristors, this parameter omega Tc or circuit turn off time is important. So Tc given by, so this is 2 pi minus pi. So that is equal to pi by omega, or you can write omega Tc equal to pi. So this is called circuit turn off time. This circuit turn off time should always greater than the thyristor turn off time. TQ is called thyristor turn off time. That is, this will be given by the manufacturer. So it needs some time to remove the charge carriers so that the device will be turned off. So this circuit turn off time is the time provided by the circuit to the SCR. So this should be always greater than the TQ. Next we will find the average voltage. Formula is same, only limits will change because your output voltage limit is here from alpha to pi. So in diodes we will get 0 to pi. In thyristor you need alpha to pi. So do the same calculation. So you will get Vm by 2 pi into 1 plus cos alpha. Then find the RMS value or root mean square value. Again same formula, only change in limit alpha to pi. So you will get the RMS value. So half wave rectifier with R load is very easy. You have derived average value and RMS value. Next we will see about half wave rectifier with RL load. So R and L load is there. So what is the property of L? So it is an energy storing element. So you cannot make the current through the inductor to become zero immediately. So it needs a path for the current to flow. You cannot, that is during negative half cycle, you cannot make this current to become zero immediately. So current continues to flow. So thyristor also continues to conduct in the negative half cycle, or till the current becomes zero, thyristor conducts. Half wave rectifier. So in this is the supply voltage. First you see the current, load current I0. So from alpha it starts to increase, then after that is after pi it decreases and becomes zero at beta. So this is beta. Okay. So you see the output voltage waveform. So till alpha output voltage will be 0. After that it will follow the input voltage waveform till beta. In case of R load, here itself it will get stopped, but due to the presence of inductance, current is flowing till beta, so output voltage exists till beta here. Then we will see the voltage across the thyristor. Again in this period thyristor is not conducting, so it is equal to supply voltage. After that it is 0 till beta. After that it will follow the input waveform. Okay. So in this case also this one circuit turn off time is 2 pi minus beta by omega. So this is 2 pi minus beta by omega. So let us find the value of beta now. I into R plus L into d by dt is equal to Vm sin omega t. Find the solution for this one. So I naught is equal to, you will get this equation. So let us apply the boundary condition and find the value of A. So boundary condition is at omega t equal to alpha, I naught equal to 0. You substitute this, you will get I naught equation. Then another boundary condition, apply at omega t equal to beta, I naught is 0. So you will simplify, you get this equation. You solve this equation to find what is beta. So this is not easy to solve. You can use some computer to solve this equation and find the value of beta. So let us find the average voltage for this waveform. Again alpha to beta is the limit here, because output voltage will exist from alpha till beta. So limits alone will change, remaining things are same. Again RMS voltage, limits alone will change. And if you simplify, you will get the RMS voltage. Now in this RL load, output voltage is becoming negative. So what happens? Average voltage. If you find the average voltage, it decreases compared to the previous case. And if the beta increases, it means that the inductive part is more, beta increases, so average voltage decreases. And because of that, efficiency is low, because we don't want a rectifier to have a very low output, and load performance is poorer. So what we can do is, you can use the freewheeling diode, which helps to remove this negative part, and thereby average voltage will increase. So points to remember here are: control rectifier, output voltage can be easily controlled by varying the firing angle. So here thyristors are used. They are called phase controlled rectifiers, and in case of AC supply, natural commutation occurs. So these are some of the references, and if you like the video, do subscribe to Read Electric Vehicle. Thank you.